Each reaction has its own equation that gives its rate as a function of the reactant concentrations. So this is called the rate law. The general form for the rate law is the rate is equal to a constant K, which we can determine through experiments, times the concentration of A to the power of X and then B to the power of Y, where A and B are concentrations of reactants. This would be for the equation A plus B, giving products. And X and Y are the rate orders, which we are also going to determine through experiment. To determine the rate law then, we have a couple of things we need to figure out, which is the rate constant and the rate orders. We need to do this by measuring the rate at different starting concentrations of the reactants. The exponents in the rate law tell us what the order of the reaction is with respect to each reactant. For example, the rate equals K A squared times B. We would say that the reaction is second order with respect to A because it has an exponent of 2, and we would say it's first order to B because it has an exponent of 1. To figure out the overall reaction order, we can find this by adding the exponents on the reactants in the rate law. In this example, if we add 2 plus 1, that would give us a third order reaction. Here's a sample problem then. We want to determine the rate constant and the order of the reactants. In terms of this problem, A is our NO and B is our O2. We then want to figure out an expression for the rate law and figure out the value of the rate constant. The way that we're going to approach this is first we need to figure out what the exponents are. So how the rate changes with respect to each reactant. Let's take a look then. Let's call these experiments 1, 2, and 3. We're going to take a look at experiments 1 and 2 first. In 1 and 2, NO is constant and O2 is changing. The concentration of O2 is changing by 0.5 divided by 0.25, or by a factor of 2. If we look then at the rates, the way the rates are going to change is going to depend solely on the concentration of the oxygen. So if we do the same thing here, if we divide them, then we would also get 2. To figure out the order, we want to take the base here of 2, and we want to rewrite how our rate changes to the same base. If we were going to rewrite 2, that's the same as saying 2 to the power of 1, meaning that the order with respect to oxygen is 1. If we look at experiments 2 and 3, let's pick a different color, then NO is changing and O2 is constant. The rate is going to then change dependent solely on the NO concentration. That is changing by 0.40 divided by 0.20, which is 2. And then if we look at what happens to the rate for those same 2 experiments, it goes up by a factor of 4, which is the same as saying 2 to the power of 2. The order of our reaction then, with respect to NO, is 2. That means that our rate equation we can write as rate equals K, concentration of O2 to the power of 1, but we don't need to put that in because it's only a power of 1, and then the concentration of NO squared. The last thing we need to do is find the value of K. To find that, we're just going to pick one experiment. Let's pick experiment 1, plug in the values into our rate expression, and then solve for K. We've got 1.6 times 10 to the minus 3 is equal to K times 0.5 times 0.40 squared. If we were to solve that, we get 2.0 times 10 to the negative 2. And then we need to figure out the units for our K based on the units that we have in our expression. Rate is always given as moles per decimeter cubed per second. For O2, it's going to be moles per decimeter cubed. And then because the NO is squared, it's going to be moles squared per decimeter to the 6. What I want you to do is use these units to figure out what the units of K is going to be. You should get decimeter to the 6, mole to the minus 2, second to the minus 1. The last thing we need to do with rate laws is just go over some general shapes of graphs and what they look like. If we have a zero order overall reaction, we looked at concentration versus time, it would be a straight line with a decreasing slope. If we were to plot the rates then versus concentration, it would be a straight line. The units of the rate constant would be moles per decimeter cubed per second. The graph changes a little bit. For a first order overall reaction, concentration versus time is a decreasing curve. If we were to plot the rates, so we're taking the rates at each point on our concentration versus time graph, and we're graphing that versus concentration, it would be a straight line with an increasing slope. The units for K with a first order reaction would be seconds to the minus 1. One thing we need to talk about is the half-life of a reaction, and we're only going to find half-lives of reaction for first order overall reactions. Half-life then is defined as the time required for 1/2 of a reactant to react. If we look at our graph here, here's our time 0. We've got 150. So half of that is at 75. And what we're looking for is the time that it takes for half of that to react. We can calculate that using this formula here. There's no need to know how to derive this formula, just to use it, but if you would like me to show you how to derive this in class, I will do that. The T half, this is our half-life, is equal to 0.693 divided by the rate constant. The last type of graph that we need to talk about are second order overall reactions. They look a lot like first order reactions, decreasing curve, but the curve is much steeper than for a first order reaction. If we were to graph rate versus concentration, we'd actually get this curved line here. But if we were to take rate versus concentration squared, we'd get a straight line. The units for a rate constant for a second order overall reaction is going to be decimeters cubed per mole per second.